Electrical noise is a very important area to understand in electronic engineering. It can distort a signal, leading to incorrect and potentially dangerous results. Understanding electrical noise, its statistical nature, and why it is caused is the first step to understanding methods of reducing noise and error correction methods. It can also give you an understanding of why digital signals are preferable to use where possible, instead of analog signals. Noise is statistically random. This is a key point to remember, as you will see later on in the video, as many mistakes are made when this is forgotten. If you look at this analog signal, you can see that random fluctuations creates a spiky effect on the signal. If you have listened to the radio, you may be familiar with the crackle in the signal that shows just how slight changes in a signal can completely distort the original message. If we compare this to a digital signal, here you can see that we have a square wave. A digital signal will only ever be a 0 or a 1. There are no in-between values. This does not mean 0 volts and 1 volt. The exact voltage level can vary, but is often 3.3 volts or 5 volts in practice. Even though there are small fluctuations of noise in the digital circuit, it is clear that it would require a very large spike to mistake a 0 and a 1. So, you should be able to see that analog signals are easier to distort and digital signals are more robust. Now, let's delve into the types of noise. Firstly, we have Johnson noise. This occurs due to the random motion of electrons in response to thermal effects. If you have heard that temperature is an important consideration in circuits, the reason is that you can get unwanted signals due to Johnson noise. Often, in formula sheets, the operational temperature range of electronics will be chosen to ensure long lifespan of the device and reduce noise. In order to analyze the unwanted signal, we want to obtain the voltage of the noise that can distort the signal. The equation shown gives us this value in volts. You can see that the Boltzmann constant, the temperature, the bandwidth, and the resistance all feature and are contributors to this noise, noticing the units in this equation. Reducing some of these values within the equation can reduce the noise, but further understanding will aid with noise reduction. Shot noise is the other type of noise that will be covered here. This is caused by random fluctuations within conductors, but there is a more complex reason for this type of noise. Here, the equation which is shown gives the noise as a current. You can see that the electron charge, the current in the circuit, and the bandwidth are the main contributors to this type of noise. It is important now to return back to the statement made earlier in the video. There is a statistical nature to noise in an electrical circuit. Hopefully, the notion that fluctuations in the signal are random and independent should trigger some memory of math statistics classes and how these two terms have an effect on the exact process of evaluation. So with this in mind, if you were to say that the total noise voltage was just an addition of all noise sources, this would be incorrect. Noise does not occur simultaneously, and it doesn't influence more noise as it is random and independent, so you can't treat the signal as if this isn't the case. To combine the noise into an overall total, you have to take the square root of the sum of the squares of the noise voltage sources. This much better reflects the statistical nature of the noise. You may be wondering what you do with the shot current, but it is as simple as converting into a noise voltage by using Ohm's law, V equals IR. Hopefully this video has given you an overview of electrical noise and explained some of the common areas in which common mistakes are made. If you found this video helpful, please like and subscribe, and check out our other videos to learn more about electrical and electronic engineering, including digital electronics, circuit analysis techniques, embedded systems, and more.